Hello, good morning. Welcome to this lecture. Do let me know if my network is good. If there are issues, please let me know and I can change. So we've been looking at we were looking at some medium scale integrated circuits. We are done with that now, and we are going to start on I think that's chapter 11, interfacing with the analog world. That's what we want to start with today. I'm just going to share my notes. I know that some of you somehow still don't have groups. There is not that's not something I can change. But I know you're submitting tomorrow. I will deal with the groups after. Anyone who has no groups, just let tomorrow pass and then we can talk on Monday maybe. I'll be sending out another assignment as well, so please look out for that. Now I hope you can see the slides. If you can see the slides. So we are going to start with interfacing with the physical, with the analog world. Now you know that the world is generally, not generally, it's typically analog. Anything you can think of is typically analog. Time, some of the signals that we can think about, or some of the phenomena that we can think about are typically analog. Time is analog. Pressure, temperature, humidity, mute, humidity, light. There are so many phenomena, moisture, you know, anything that you can think about is typically analog. However, we work with digital circuits. So that means that we need to find a way of converting these analog values or analog phenomena into some digital format that we can work with. And usually so for instance, if you are dealing with, you are processing something with a computer, think of a scenario where you are controlling the temperature of a room or regulating the temperature of a room or some chemical process using your digital system like a computer. That means that you need an analog sensor that picks up the signal from the room. That is a temperature measurement. It needs to be converted into a digital signal or a digital message that your computer can work with. And then after that, you do your processing and your control. And for instance, if you choose to control that temperature, maybe you want to, either it's below the threshold, you want to switch on the heater, or it's above the threshold, you want to switch on the fans or open the windows, you need to convert it back into an analog format. So we know that with digital systems, the value usually does not matter. If, for instance, you look at TTL logic, these are the TTL devices, any value, any voltage that is between 0 and 0.8, any value that is between 0 and 0.8 is digital logic 0. Okay, so we just take it as 0, whether the voltage is 0.5, 0.2, 0.7, 0, all of them, we refer to them as logic 0. And if it is from 2 to 5, this becomes digital logic 1. So in the digital world, the actual value then does not matter. All we want is to make sure that that value is within the range that is representative of the digital state that we want. However, in analog, it's very important, and we are going to see it later on in this lecture, perhaps the next one, how we actually deal with this scenario where in the analog sense, the value of the voltage actually matters, because that is exactly representative of the prevailing phenomena, value of the phenomena we are measuring. However, in the digital world, the whole range means the same. Now, there is this one that is somewhere between 0.8 to 2 volts. This is, sometimes you can say it's indeterminate. In other words, we shouldn't be in there. But remember, I think in our last lecture, we talked about a state high Z, tri-state high Z. Usually the high Z is within there, or the tri-state. The third state, usually that doesn't mean either logic 0 or logic 1, is within there. Anyway, so in the real world, we measure a physical variable. Okay, this is the real world here. So this is either a temperature value, a digital, an analog temperature, humidity, temperature value. And we have this piece of electronics that we call a transducer. Now, generally, a transducer converts something, anything. It converts one form of energy into another. In this case, we have temperature, which is a form of energy. And usually, because this is an electronic system, we are converting whatever it is here, we are converting it into an electronic signal. That electronic signal is then the one that we can apply to our electronic system, our digital system, even analog system, whatever we are doing. You need to first convert pressure, whatever that pressure is, into a representative electronic signal that can flow on the wire. Now we have an electrical analog signal. So really this transducer converts your physical phenomena in whatever form it is. It could be temperature, pressure, humidity, all these things mean they are in different forms, and converts them into an electric signal. So it might say that temperature of say 20 degrees centigrade, it will convert it into 2 volts or a current, and 30 degrees centigrade, it might convert it in 2.5 volts. And so this is the process of transducing. After that, we have an analog to digital converter, because now we have an analog electric analog signal. We convert it into a digital format, but we do that to ensure that our digital output is an equivalent of that analog signal. Now remember, the analog signal value is important. So we are not going to have ranges representing analog signal. And so we convert that into a digital signal and pass it through our electronic system, our digital system, and do whatever we want to do. Usually, that's not where we stop, because we want to do a process or some activity that we call actuation. And so we need to convert, after processing, we need to convert back into the analog, an analog signal, and we use a digital to analog converter. This is an analog to digital converter, and that's a digital to analog converter. Now, these are really representative based on their names. It's very easy to know which is which. Digital to analog converter gives you an analog signal that is equivalent of the digital input. This is the digital input into the DAC, or the digital output out of that digital system. That goes into that, and usually that feeds the actuator. Now the actuator is actuation is trying to change a physical phenomena. And so the actuator here is something that can change whatever current state of affairs is. Now, when your temperature is low and you switch on the heater, you are actuating, and so your actuator here is the heater. If the temperature is high and you switch on a fan, you are actuating the temperature, because you're going to reduce it, and that process. So the process of actuation really is like regulation, but it could be wider depending on different contexts. Okay, please, when you have a question, do text, do write in the chat. We are going to go into the examples. So we are going to start with a digital to analog converter. Now, if you look here, the digital to analog converter is actually on the output side of this diagram. However, we start with it because usually most analog, we should ideally start with an analog to digital converter, but most analog to digital converters include a digital to analog converter. So we need to first understand this because it is also applied within the ADC, right? That's why we begin with a digital to analog converter. Now a digital to analog converter obviously has digital inputs and analog output, obviously. So the input is digital, the output is analog. Now these are your digital inputs. As we can see, this is DCBA. We know D is the most significant bit. You could call this a 4-bit DAC because you can see it has 4 bits going in. We are going to have 2-bit DACs, 8-bit DACs, whatever. But yeah, that is how you can, if I say 4-bit DAC, I mean you have 4 bits going into the digital analog converter. And you have one analog output. And that analog output is an equivalent of the digital input, whatever that digital input here is. So you could say if my digital input is 0, 0, I'll have an analog output of 0 volts. If maybe it is 1, 0, 1, 1, I might have 3 volts, etc. Whatever you have here has a corresponding equivalent in analog terms. Now we have this, and I should explain this. The reference value is actually the full scale value. So it is the maximum output analog signal. So this DAC has a maximum output of 16 volts. In fact, it is 15 volts. I think this is a mistake. It should be 15 volts. This digital analog converter can produce an output analog signal of 15 volts maximum. We call that the full scale output, or you can say full. You can even do that. So we can say therefore that depending on what we have at the input, we get a corresponding output. We can say that our analog output therefore is equal to a certain proportionality K times the digital input. This K can be any number. It can be big, it can be small. It can't be 0, but it is usually a finite number greater than 0, but usually not so big. Usually less than 0, in fact, less than 1, sorry, not less than 0, but less than 1. Now, this means that we know what the digital input is and the analog output, and so there is a proportionality there that relates the two. If we look at this case, let us look at a scenario like this. When we have 0, 0, 0, we get 0 volts. When we have 0, 0, 1, we get 1 volt in the digital. This is analog. If our inputs were 0, 0, 1, 0, we get 2 volts, and so on and so forth. And so you can see this is really just binary conversion, straight binary into decimal. So you can see that 0 on the analog, 0, and we can say this is equal to 0 times 0, sorry, K times 0. This one is equal to, if K times digital out input. The digital input here is 1 because the rest is 0. So K times 1. You'll notice, for instance, here, digital input is actually 7. So we have K times 7. And if we look at a scenario like this one, we have that's 8, 10, 11. So 11 is equal to K times 11. Therefore, it's easy to conclude that K is equal to 1. The proportionality here is 1 because the digital input is equivalent to the analog output. If your digital input is 7, the output in analog terms is 7. If your digital input is 15, the analog term is 15. The reason why I say this is 15 is because, as you can see, the maximum, when everything is 1, you have your maximum digital input, and that usually is equivalent to an analog output full scale. When everything on the input on the digital side is 1, 1, 1, 1 throughout, then on the output analog signal, you should get a value equivalent to the full scale. And we can see here that when we have 4 bits, our full scale is 15, which should be equivalent to VREF. So it is easy to see that analog signal is equal to K times digital input. And K has units of volts. We can see that because if we have, say, take this example, if our analog is equal to K, which is 1 volt, times input of, that is 5, which is 5 volts. Okay, let us look at some examples. Here we have a 5-bit DAC, which has a current output. So this one has a current output. For a digital input of 10100, the output current is 10 milliamps. So we are saying, what will the output current be for a digital input of that? Let us first look at this one. This is 2 to power 0, 1, 2, 3, 4, 2 to power 4 plus 2 to power 2, because that is 0, 0, 0. And this gives me 20. Now, you can see that it's a 5-bit DAC because it has 5 bits. Now the output is 10 milliamps, and the input, this is the digital input. The analog output is this, 10 milliamps. So we can say that our 20 times K is equal to 10 milliamps. You can see that the digital input is the one we multiply. And so K is equal to 10 over 20 milliamps, which is 0.5 milliamps. So this is our proportionality factor. Now the new digital input is 11101, and this is 2 to power 4 plus 2 to power 3 plus 2 to power 2 plus 2 to power 0, which is 16 plus 8, 24, 28, 29. This is our digital input, and so our analog output, corresponding analog output, will be 0.5 milliamps times 29, which is 14.5 milliamps. As simple as that. If we look at the largest, this example now, what is the largest value of output voltage from an 8-bit DAC that produces 1 volt for a digital input of that? 00110010. So this is 2 to power 0, 1, 2 to power 1, 2, 3, 2 to power 4, and 2 to power 5. This is equal to 32 plus 16 plus 2, which is 50. So this 50 in digital corresponds to 1 volt in analog. So we can say that 50 times K is equal to 1, or K is equal to 1 over 50. Obviously, this is going to be V here, volts. Now, what is the largest value of output voltage? The largest value is full scale value. And since this is an 8-bit DAC, full scale is equal to 2 to power 8. I think 2 to power 8 minus 1. We are going to look at this, which is 255. Okay, because it's basically 1, 2, 3, 4, 5, 6, 7, 8. So 2 to power 7 plus 2 to power 6 plus 2 to power 5 plus 2 to power 4 plus 2 to power 3 plus 2 to power 2 plus 2 to power 1 plus 2 to power 0. I think it will give you 255. And so our full scale is 255 times K, which is 1 over 50, which is 255 over 50 volts. And I don't know what that is. It is 5.1 volts. Okay, thank you, Godfrey. Now, this is really simple mathematics, and actually this chapter is quite simple. Everyone should be able to find it quite easy. Now, we have seen, let us look at an example. If we are just make a reducted version of this, let's consider, say that we are doing a 2-bit DAC, B, A, V out. It is 0, 0, 0, 1, 1, 0, 1, 1. So here it's 0, 1, 2, 3. As you can see, we can see that V out, which is the analog equivalent, can either be 0 or 1 or 2 or 3. So we have our digital input and we are converting it into an analog. So we expect that what we get at the output of the DAC is an analog signal. But look, it can only jump from 0 to 1, 1 to 2, and 2 to 3. In other words, this also isn't quite an analog signal, as we know that an analog signal is continuous. We shouldn't be, this one is a step function. It can only change in those steps. So it's essentially similar to a digital signal. And so that is a big problem. But what we do is that if we increase the number of, we are going to look at some ways of making this signal on the output as close to actual analog as possible. There are some mechanisms, but it's better to maybe refer to this signal as pseudo analog. A pseudo analog is something that seems like analog, but is not quite analog. Another thing that I want us to look at is input weights. Now, as you can see, D, C, B, and A contribute to the analog signal. However, each of them contributes a different value. So if we had 1, 1, 1, 1, this one will contribute 2 to power 0, this contributes 2 to power 1, this one contributes 2 to power 2, and that contributes 2 to power 3. If we are looking at the full scale, we would say that D contributes 8, C contributes 4, B contributes 2, and A contributes 1. These are the weights of these inputs. A low significant bit has a much lower weight than the the most significant bit, and the other one in the middle, obviously, as you can see here. And so you can see that when A is 1 and the rest are 0, your output is 1. If B is 1 and the rest are 0, your output is 2, and so on. And so D is 1 and the rest are 0, output is 8. And these are the so-called weights of these bits. The most significant bit has the largest weight, and the low significant bit has the smallest weight. We should also note that each weight doubles as you move leftwards from the low significant bit. So your low significant, if you know the weight of the low significant bit or the lowest significant bit, you don't need to calculate the weights of the most significant bits, because you can just keep doubling as you go towards the most significant bit and get the corresponding weights of each of those bits. Now let us look at a 5-bit DAC, and we are going to use this. We can use this method to do the calculations that we've just done. We have a 5-bit DAC that produces V out of 0.2 volts for a digital input of 00001. This one gives us 0.2 volts. We should already see that this is the weight of the low significant bit, because the low significant bit, the weight of the low significant bit is measured when the low significant bit is 1 and the rest are 0, as in this case, or as in this case. And so 0.2 volts is the low significant bit weight. Good. Now find the value of V out if we are having an input of 1, 1 when everything is 1, 1. In other words, that's full scale. So we can say that weight of bit of A 0.2, B will be double 0.4, C will be double that 0.8, D will be double that, which is 1.6, and E will be double that, which is 3.2. And so now the full scale is the sum of these weights. So when we want to get the full scale, we sum up those weights, which is 3.2 plus 1.6 plus 0.8 plus 0.4 plus 0.2, which is equal to 3.2, 4.8, 5.6, 6.2 volts. Okay, thank you, Sylvia. Now, if I wanted to find what if E, D, C, BA was 10110? All I need is to add the weight of E, jump that, add the weight of C, and add the weight of B. And that would be 3.2 plus 0.8 plus 0.4, which is 4.4 volts. This is how I would easily do that. And maybe let me just introduce a new slide. I could also have done this using our earlier input, which was that K times digital is equal to analog. And since this is 0.2, and digital is 1, my digital input is 1 that is corresponding to that one. It would be 1 times digital input. What am I doing? Yeah. So it would, I know that the digital is 00001 and the analog is 0.2 volts. So my K would be analog over digital, which is 0.2 over 1, which is 0.2 volts. Now, if my digital input is now 11111, which is the case for this one, then I know this is 31, I think. Yeah, because this is 16 plus 8 plus 4 plus 2 plus 1, so 24, 28, yeah, 31. And then my analog would be equal to now 31, which is the digital, times 0.2, which should be giving me, I believe it should be giving me 6.2 volts. And the other case that we have done, which is 10110, is 16 plus 8 plus 2, which is 26 input. This is input, meaning that my analog output is now 0.2 times 26. What do I get? Do I get 5.2? I don't get 5.2. That is 10110, which is 16 plus, so I made a mistake. It is 16 plus 4, because the 8 is 0. It is plus 4 plus 2, so it's 22. And 22 times 0.2 is clearly 4.4. So we can use this method of the calculation, or we can use this method of the weights to perform our calculations. Either method is fine, unless obviously I specify. If I specify, I would usually be specifying that you use the weights. I cannot specify that you should use the calculation method. But if I don't specify, please use whichever method you want to do your calculations in. Okay, since there are no questions, we can continue. Let us look at something that we call resolution. I think you know what resolution is in general, because It's an English word actually, and the Namagunga people will know this very well. But typically, resolution is the smallest change that can occur in the output if the input changes. And we know how the input changes. Obviously, the input change that causes the smallest change in the output should also be the smallest input change. If you have your smallest input change, it causes a corresponding smallest output change or change in the output. Now let us look at something like this. We already saw our digital to analog converter. In this case, we have a 4-bit counter that is feeding it, and so we know how counters work. It is 0000 all the way to 111. And then it loops back to 0000 and all the way back to 1111. Now here we see that the resolution is 1 volt. It means that if you change the input through the smallest change, it causes a corresponding small change in the output. Now we've been told that the smallest change in the output is 1 volt. So that means if I move on my side of the counter, if I move from 0000 to 0001, that is a change of 1. On my analog side, I will also move a change of 1. And this may be from 0 to 1 volt to 2 volts. And really, without going far, we have a similar scenario as this one. Remember this truth table where we were having corresponding values equivalent to that. So we start at 0. That means that as the counter counts from 0001, we'll go to 0010, 0011, and so on. And so as we move from this step to that step, we change by 1. We are going to change by 1. To the next step, we change by 1, all the way up to 111, where we change by 1 and we jump back to the start. Now this causes a stair function, or a so-called staircase function. We are going to start at 0, and the next count will take us to 1 volt. The change will be 1 volt, which is really the resolution. And then the next count will take us to 2 volts, 3 volts, 4 volts. We can see that every time we get a change of 1 on the input, we get a change of 1 volt on the output. And that is the resolution. And we've been given the resolution here, and so on and so forth. So we are going to change all the way through staircase function until we reach 15. This 15 corresponds to 1111. Obviously, this 0 corresponds to 0000. Now we know that when the counter reaches 11, if it flips back to 0000 to start the count, and that's why this drops back down to that and starts the count once again. So we can see 2 aspects here. I'm going to make a duplicate of this. We see 2 aspects here actually. Let me first remove that. The 2 aspects we see are levels and steps. Now here we have how many levels? We have 16 levels. From 0 to 15, those are 16 levels. We have that, and so on up to 16. However, the steps are 15. The steps are 15 because you start at 1 step. And so when you are still at 0 steps, you are already on 1. Sorry, when you are still at 0 jumps or steps, you are already at 1 level. Well, there's no 0 steps, you know. But you can see that we have 16 steps. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. However, the jumps or the steps that are between them, which is this one, 1, 2, 3, will be 15. Now this is equivalent to 2 to power n, whereas this is equivalent to 2 to power n minus 1, because n here is 4, so it's 2 to power 4, which is 16, or 2 to power 4 minus 1, which is 15. Now, if we want to get the resolution, The resolution, we know that the full scale is 15. Full scale is equal to 15, but our resolution is 1 volt. We know that our revolution is 1 volt. How do we get that? We can say that 1 is equal to 15 over the number of steps, which is 2 to power n minus 1. Okay, so this is also going to give you 1. So the resolution formula is actually resolution, and I'm sure now by now you had already noticed that this is K, because the resolution is the proportionality factor. It says that if they change this side, how much do I change? And really the resolution is the smallest change. You can change by a bigger value, but that's not the resolution. The resolution is the smallest change. So for instance, if I jump from 0000 to 0110, I've jumped several steps. And so my DAC should still be able to give me the right output. But if I want to check what the resolution is, I need to be able to jump only one step at a time. So maybe 0000 to 0001 or 0111 to 1000. You know, this is the change that is going to give me the resolution. And so therefore, it is okay to say that our resolution, which is equal to K, is the full scale output, AFS, over the number of steps. Because we are looking at not the number of steps, yes. We are looking at how many steps we need to reach the full scale, and that is our resolution. Okay, let us do an example. Okay. Right. So we have an example here which says that a 5-bit DAC we have a 5-bit DAC or digital to analog converter that produces 0.2 volts for a digital input of 0.0. This is the example that we have already looked at with the weights actually. This gives us V out of 0.2 volts. That is our, this really we need to know as our resolution, because it is the K, it is the lowest weight, it's the lowest significant bit weight. For an input, find the V out for an input of, we have already found that one, I think it was 6.2 volts. Or something like that. Now, what is the resolution of the DAC in this example? It is example 11. Describe the staircase signal of this DAC. Now, in this case, this is a 5-bit DAC. And so its number of levels are 2 to power n, which is 32. And its number of steps are 2 to power n minus 1, which is 31. So describe the staircase signal of this DAC. So the staircase signal will increase from 0 volts. Every time it will jump 0.2 volts, okay, 0.4 volts, and so on, until it reaches its maximum full scale voltage of, which was 31 times 0.2, which was 6.2 volts. And so you have many steps here until you reach 6.2 volts, and it will come back down to, and so on, all the way back to 6.2 volts. Its resolution, as we have seen, is 0.2 volts. As simple as that. Let's have another example. We have a 5-bit DAC. Okay, maybe determine the V out for a digital input of 1001. We already know how to do this stuff. It is V out, which is K 0.2 times V in, which is times the digital input, which is, this is 2 to power 4 plus 1, because this is 2 to power naught, that is 2 to power 4. So this is 17 then. 0.2 times 17 is equal to, that is equal to 3.4 volts. All right. Any questions? Yes, Godfrey, we do put units on the resolution. I think it depends on the context, but yes, resolution has input. So you could say that resolution is equal to 0.2 volts per step. Okay, and then for full scale, we need 31 steps. So then we have 0.2 volts per step times 31 steps, which so you'll find that it depends really on the context how you put the units. They need to be able to make sense. Yes, Frederick, I'm aware that there is a computer engineering class at 11. We are going to continue. I see here that we have about 93 students, so this is quite good attendance. I know you are supposed to be about 150. I know that we are going to get many retakes, but it's good that the numbers are increasing to now near 100. When the computer people go, I totally understand, and that's fine. The staircase signal is maybe I may not even bring a question like this, how to describe the staircase signal out of this of the dark. But I think when you want to describe it, you want to describe it in terms of three things: number of steps, resolution size, and number of levels. If you can find out what these three parameters are, I think then that's really fine. You can describe, you will probably have described the staircase signal. And we know number of steps to be 2 to the power n minus 1, number of levels to be 2 to the power n, and the resolution size is obviously a full scale over 2 to the power n minus 1. So we would have all the information that we need. When increasing the steps, we increase by k or we double? Richard, I don't know what you mean, but if we want to increase the number of steps, we should increase the number of bits. So we are going to do an example later on. Actually, we should probably just go on to it, and maybe it might throw some light on what we are trying to do here. So we do have something that we call percentage resolution, and this is where we express the resolution as a percentage of the full scale. Okay, so we know the resolution to be the step size. This is your 0.2 volts per step. This is your resolution. We divide it by the full scale and then put it in percentage form. So if we were here, we know that our full scale is, we got 6.2 volts, I think. So our percentage resolution here would be 0.2 over 6.2 times 100%. What is that? Anybody? It is 3.2, 3.2%, which is okay, which is 3.2%. What this really means, this means that every time we jump 3.2% of the full scale. So depending on what the full scale is, each jump we make is 3.2% of that. So the next, if we make our first jump, we have gone 3.2% towards the full scale. The next jump takes us 6.4%, the next one 9.6%, the next one 12.8%, and so on and so forth, until we reach a jump that puts us at 100%, and that jump would, that level now would be the full scale level. So I think the percentage resolution is a very important parameter, because it's not just a value, it is a ratio. You know, ratios are really important because they compare two things. If I tell you my resolution is 0.2 volts, it doesn't give you much information. But if I tell you that my resolution is 3.2%, it gives you a bit more information to understand whether that is a big jump or a small jump. Now, let us look at another example. We have a 10-bit DAC with a step size of 10 millivolts. That means our resolution is 10 millivolts. Determine the full scale. Full scale is equal to, as we said, you remember we had an interesting equation which was K is equal to A full scale over 2 to the power n minus 1. So we can use that equation to say that full scale is equal to K times 2 to the power n minus 1, which is equal to 10 millivolts times 2 to the power, this is a 10-bit DAC, minus 1, which is, this is 10.023. So we have 10.23 volts. Now, what is the percentage resolution? Percentage resolution is equal then to our resolution, which is 10 millivolts over 10.23 volts, which is equivalent to 0.1%. Now, if you compare this scenario with the other one, which was 3.2%, this 3.2% was a 5-bit DAC. For a 5-bit DAC, you have to make big jumps. For a 10-bit DAC, you can see you are making very small jumps. Every time you jump only 0.1% of the distance towards the full scale. So you could say that by increasing the number of bits, we are making our pseudo analog signal as close to analog, pure analog as possible as compared to this one, because this one has big jumps, whereas this one would have small jumps, and it is almost similar to an analog signal. And so, yeah, I've probably just said the point in there that if you want to get an analog output that is as close to pure analog as possible, you should increase the number of steps and not just the resolution. The resolution should certainly be small, but the percentage resolution is what is most important. It needs to be very small. So I see some questions. Abuda Emmanuel, I think everyone else is getting my voice. It must be on your side. And if you're not getting my voice, then maybe you didn't hear that. Ian Tusime, K is the resolution. Yes, K is the resolution. So the resolution is the smallest change in your output after any change in the input, which really is usually the smallest change in the input. So if you have a watch that changes from seconds, you know, you have a second and minute and hour or whatever, it means that the smallest change you can see on your watch is 1 second. That is going to be the resolution of the watch. But some watches don't even show seconds, they just show minutes, meaning that you will see 1 minute and the next change on that time is when it changes to 2 minutes. That means now the resolution of that system is 2 minutes. That would be fine if you don't care about seconds, but if you're dealing with a system which requires the seconds, then you would need to add that second so that you can enhance the resolution of your clock, of your watch. So let us take a 10-minute break, not 10 minutes. We'll come back at 11:10 a.m. and we continue. I'll see you in a moment. All right. Okay, so I'm back. Let's continue. Percentage resolution. So I have somebody helping me clean the room. I hope that you're not startled by that if you hear any noises. The other thing that we can note on percentage resolution is that actually it is also equivalent to 1 out of number of steps. So if you have 1 over number of steps, that is also a good. So for instance, we had seen that we have 10 millivolts over 10.23 volts, giving us approximately 0.1%. If we took the number of steps, it would be 1 over 1023, which is also approximately 0.1%. Okay, so that now is out of the way. Let us look at an example. We have this example from the book. We have this figure. It is a computer. So we have a computer that is controlling the speed of a motor. This is the motor speed. And so we have a signal coming from the computer. Usually that might have some input from the whatever the measuring, you may be measuring here, the speed, and then controlling it through the computer. You have a digital to analog converter that feeds a current output. We can see that this is a current output going into some current amplifier that manages the motor. And this is really an important example, so let's try to pay attention. So the question is that the 0 to 2 milliamp analog current from the DAC, this one, which is I out, is used to amplify, is amplified to produce motor speeds from 0 to 1,000 revolutions per minute. So the range is 0 to 1,000 revolutions per minute. That really gives us our sort of full scale as 1,000 in revolutions per minute. How many bits should be used if the computer is to be able to produce a motor speed that is within 2 revolutions per minute of the desired speed? You see, if we jump like this, and we are saying that we should be within 2 revolutions per minute of the desired speed, it means that that step should be less or equal to 2 revolutions per minute. That is how we can ensure that we are within 2 revolutions per minute. So for instance, I could say I have my step size, whatever that value is, let me say that value is x, that should be x plus 2, x plus 2, so that I can ensure that whatever number I pick, if I pick that number, it's within 2 revolutions per minute. If I pick that number, it's also within 2 revolutions per minute. So we could therefore say that our resolution is 2 revolutions per minute, maybe per step. Okay, each step should be 2 revolutions per minute. Now, if we have 0 to 1,000, this is our full scale. A is 1,000. How many steps do we need to reach 1,000? We would need 500 steps from 0. to reach full scale. Okay, to reach full scale. So we need to go through 500 steps. But we know number of steps is equal to 2 to power n minus 1. And so we can therefore say that 2 to power n minus 1 should be greater or equal to 500. Because we don't want the number of steps to be less than 500, because that will not take us to the full scale. 500 or more can take us to the full scale. And so if we do the math, we see 2 to power n is greater or equal to 501. We know that 2 to power 8 is 255. That means 2 to power 9, 256 actually. 2 to power 9 is 512. So 512 is the first number that is greater than 500, that is a power of 2. That means we need, our answer here, we need 9 bits. We need a DAC of 9 bits that is able to help us to take us from this, because from 0 to 2 to 4 to 6 all the way to 1,000, we can go through 512 steps. I mean, this resolution, our resolution, I should call it our resolution. This resolution is like we can use this as a maximum acceptable resolution. The resolution can be smaller, but this is the maximum acceptable. Now, once we get the total number of steps, we can get our actual resolution. I'm going to make right. I'm going to be with you in a moment if you have a question. So now we have seen that we have 512 steps. We can now find our resolution as number of steps as 1 over number of steps, which is 500. And is it 500? And those are number of levels, and 11, something like that would be percentage resolution, I think. We can say that resolution K is equal to a full scale over 2 to power n minus 1, which is 1,000 over 511, which is something that you can help me with. Okay, you're welcome. So how did you get 500? 500 is quite easy, actually. I'm just going to explain once again. Our question says that the range is 0 to 1,000. We are saying, the question says that we want to make sure that we produce a motor speed that is within 2 revolutions per minute of each other. So that tells me that my maximum, my maximum allowed jump is 2 revolutions per minute. This is revolutions per minute as well. So how I know this is because you want to be able, if I give you any number, it should be within 2 revolutions per minute of what the analog signal is going to give you. Remember we said earlier that the analog signal is pseudo analog, so it also jumps in steps of 2 revolutions per minute. And so that's why I took this. Now, for me to move from 0 to 1,000 in jumps of 2 revolutions per minute, I need 500 jumps, which is really 1,000 minus 0 over 2, which is my 500. However, there is no factor of 2 to power n that gives me 500. So I've gone to find 2 to power 9 giving me 512. And I need my jumps to be at least 500. They cannot be less. So I'll take the next big number. You can take more bits, but those bits will be, it will be a waste. I could do a 10-bit DAC, 11-bit DAC, but that would be a waste. I use 9-bit DAC. These are 9 bits. And this will take me through 511 jumps or steps to give me my A full scale of 1000 revolutions per minute. Okay, 1.956. All right, I think I went off, right? I think I went off briefly, so I'm back. Hopefully you can hear me. Ian was asking, how do you know that the 2 is the resolution? I mean, 2 is the question tells you that whatever number you pick, it should be within 2 revolutions per minute of what the analog output is. Remember, the analog output is pseudo analog. It jumps in steps of 2. So how do you ensure that if I come up with a random number, it will be within 2? You know, if you subtract it from whatever you have, it will be within 2. That really, if you interpret the question, that tells you that the maximum accepted jump is 2 revolutions per minute. But that is not necessarily the resolution. Once you choose the number of bits, it may give you a bigger number of steps, and then you calculate backwards and get the actual revolution. What if I may use 1.5? You cannot use 1.5. 2 has been given to you. If you use 1.5, I think you will end up requiring more steps. Okay, but it's not necessary to use 1.5. But if you use it, you will need more steps. Okay, sorry, you will need more bits because you have used more steps. If you're jumping, now we have seen that, for instance, our resolution is now 1.956, I think, revolutions per minute per step. And this corresponds to 512 steps and 9-bit DAC. The other question is, using this DAC size, how close to 326 revolutions per minute can the motor speed be adjusted? How close to 326 revolutions per minute can the motor speed be adjusted? You see, this is all a consequence of the fact that the analog signal that is at the output is not actual analog, it's pseudo analog, it jumps in steps. However, from 0 to 1000, I could say 0 to 1000, you are jumping in steps. You see? And you're moving like this until you reach 1000. Now let us assume that this point is 326. The question is, and yet you can only be at this point and at that point and at the next point and so on. So this question is saying, how close to 326? If this is the level for 326, you want to find that gap and see which of the 2 is closer. And you will choose the level that is closest to 300 and 26. We know that we start at 0. Let's say we have these levels. We start at 0. The next one is 1.9656, I think. That's our resolution. 1.956 plus the next 1.956, and so on. We keep moving until we reach 1000 based on this after 511 steps. So if we use our formulas, we will find that the number of steps that take you close to 326 is 326 revolutions per minute over 1.956 revolutions per minute per step. You can see that what comes out of here is in steps. And I don't know how many steps those are. So 32, yeah, which is 166.67 divided by 511, but it should be, this should be 57. I mean, it is 569, so it should be 57. And so we can have 1.57 here. I don't know if that changes anything. Yeah, so this is now just 6, not 67. So 166.6 steps. Now you see, this will take you to 326, but this is a fraction. You cannot have a step that is a fraction. So either we have 166 steps or 167 steps. Now 166 steps, you see we have 1.66. Sorry, 166.6. So ideally we are closer to the 167 step than the 166 step, technically speaking. So let us say 166 times our revolution is 1.957 gives us, and then 167 times 1.957 gives us 1.957. This will give us 324.9. 1.957 times. This one will give us 326.8. Okay. Right. So in these steps, now our reference is 326 revolutions per minute. Which of these two values is closest to that value? It is this one, I think, 326.8, which is 0.8 above. This one is actually 1.1 below. And you can see we could, I just did the two steps just to show you how it looks. But I think without doing both, you could already tell that since 166.6 is closer to 167 than 166, the step 167 is the one that brings you closest to the value that I've talked about. So I think the question was how close to 326 can the motor speed be adjusted, and how close is within 0.8 revolutions per minute, and the step is 167 step. Okay. Yes, great. So that was an interesting example. Let us look at some circuitry, and hopefully we can finish the circuitry. Now, we don't really need to know the circuitry within the DAC, but I think it will help us to appreciate some few things. But these DACs can be picked off the shelf as packages or even integrated circuits. And so usually you don't need any circuitry knowledge to understand what is going on in there. But here we'll just go through it and maybe you can do a bit of reading on your own. Now, this is how a DAC looks like if you look at the circuit level. We have our MSB here and our least significant bit here. Now, we generally know based on the weights that the least significant bit contributes less power than the most significant bit. It contributes less to the output than the most significant bit based on the weights. And so that's why you see the resistance on these lines increases as you go towards the least significant bit. Here you have 1 ohms. These voltages could be different. These are just in the example. Here you have 2 ohms, which doubles. Here you have 4 ohms, which doubles, and then another double to. That means that the power at A contends with a lot more resistance than the power, the power at D. And these can be either 0 or 5. We are going to talk about this. This should be either 0 or 5 because now you see this voltage is going through the resistance. So what we get out on the output is quite specific. The question is, if we said in digital that 2 to 5 is the same as logic 1. The problem with this is that if you put 2 here, then you have 2.5, 3.9, 2.8. That is not really going to work. We need to find a way of generating pure 5 volts or pure 0 volts. And we are going to look at how that works in a moment. Now, this is called an operation. This is an operation amplifier, which actually is a summing amplifier. Now, I don't teach amplifiers, so don't dwell on this. But what we need to know is that for each of these, the value on the output here is the value on the input, which is D input, or should I say voltage D input, times RF over Rin. That is the value that comes to the output. And so usually we say that V out is equal to, I can say, and it produces a negative value, but the negative, we don't care too much about that. That we can always remove the negative if we want. V out is going to be negative VD, the input here. That could be 5 volts or 0 volts. This could be either 5 or 0, okay? Whatever that is, depending on if it's a 1 or a 0. V in times RF over, I could say, times RF over RD plus VC, the negative is outside, VC times RF, RF is the same, over RC plus VB, RF over RC plus VA, RF over RA. This is B. And then you have minus RF, because it is, and that is VD over RD plus VD over RC plus VB, this is C, VB over RB plus VA over RA. Okay, so that is the general equation of our V out. Now we can see that RF is 1K and the others are also K. So you can see that when we insert the actual values, it actually becomes that equation where we have, and this is really indicative of the weighting that we talked about, because you can see that the voltage at D is left as it is, but the voltage at C is halved, the voltage at B is multiplied by a quarter, and that one by 1/8. Right. Now, What is V out if DCBA is 1010? V out, we can see that D, it means that VD is 5 and VB is also 5. The rest are 0. So it will be negative VD, which is 5. It would be 5 times 1 kilo over 1 kilo really, okay? Plus VB, which is 5 times 1 kilo, but the voltage of the resistance of B is 4K. And so that goes, this goes with that. And so we have 5 plus 5 over 4, which is 1.25, which is 6.25 volts negative. But the negative sign is not so important. It's just basically it's a result of the operation of the amplifier. But for our purposes here in digital circuitry, we will not dwell too much on that inversion. We can always invert it back. So that means if we want to find the resolution of this, we can say DCBA is 0001. And then we will see that V out for this case is equal to negative VA times RA, which is RF over 1K over 8K, which is negative 5 over 8, because that goes. And VA, when it's 1, it means 5. And I think this is 0.625 volts. Now, if we come to our truth table, our resolution will be the case of this one, A being 1 and the rest are 0, which is 0.625. And then that is the jump per step. We can see that our full scale is 9.325, which is obviously equal to, since we know the resolution as 0.625, it is equal to full scale, if you use the formula, over 2 to the power n minus 1, this is 15. And so 15 times neg 0.625 should give you neg 9.375. Okay, so this is how the dark circuitry would work. There are some other darks. The problem with this one, if we changed each weight of this, we have already seen, I think. The weight, this is 1 kilo ohms, that's 1, 2, 4, yeah. So we can see that for D, it is going to be 5 volts. For C, it will be 2.5 volts. For B, it will be 1.25 volts. And for A, it will be 0.625 volt. You know, we just keep dividing by half, by 2, sorry. And these could be negatives, it really doesn't matter. But you can see that this is actually corresponding to the resolution that we talked about earlier. Now, if we changed RF to 250 ohms, what happens? If we change RF to 250 ohms, our V out becomes negative. If we come back here to this example, now VD would have been 1K over 1K, but now we are saying it is 250 ohms over 1K, which is 1,000 ohms, meaning that we are going to have a quarter. We are going to multiply a quarter throughout, which is a quarter VD plus 1 over 8 VC plus 1 over 16 VB plus 1 over 32 VA. This is a new case if we changed this to that scale. And so that means that we are going to have neg 1 over 4 times VD plus a half VC plus a quarter VB plus 1 over 32, no, 1 over 8 VA. So our V out is then neg 1 over 4 times, let's say for the case of 1111, which was 9.325 times 9.325, it will be equal to, was it 9.325? 375. Which is 2.3. This is the new full scale. 2.34375. So if we change this to that, and with the full scale is equal to 2.34375, that shows you that if RF reduces, the full scale voltage will also correspondingly reduce. Okay, we talked a bit about the conversion accuracy. We talked about the fact that voltages, ranges in digital mean the same. They mean the same. The problem here is that we need either 5 volts or 0 volts. We are not going to work well with 2 volts, 2.5, 3.5, whatever. So we need to figure out how to generate 5 volts when we mean, if we say D is 1, we need to actually generate 5 volts, a fresh peak 5 volt, volt output. So you see we have a precision reference supply, and this is kept at 5 volts. And we have these switches. The way these switches work is that if D is 1, switch closes. And if it is 0, switch opens. Now when it opens, it is not connected to that. When it's closed, it is connected to that. So you can see here that this is a type of switch that does this, and you can see here that it is, for instance, in a closed position. So if we have a 1 here, we will get our 5 volts coming through here because the switch will be closed, going in here. We will not be getting whatever voltage was here, because this could be 2 volts or 2.5, which would still be voltage, which would still be digital logic 1, but we need to generate 5 volts. If we have a 0 here, this is open, and if this is open, then we have 0 going in there, which will have no impact. If we have a 1, this closes, and we have 5 going straight through here. Remember, this 5 is also connected to here and to there, and so on and so forth. So this is important. We need to be getting a fresh and a precise 5 voltage rate, voltage output going into the summing amplifier. Okay. Yeah, I think we can finish these 2-3 slides that are left. We have a current output DAC. A current output DAC looks like this. These are similar to switches that we have already talked about. This is a switch that is closed when input bit is 1. Okay, so if this was 1, that would close there, meaning that the Vref, you have your V reference going through here. If it is 0, that is open, and so there is nothing going through that, which is what we want. You read more about this in the book, really, but I wanted you to know that I'm interested in them. So the equation is here. Our I output, it really looks almost like the first circuit that we saw, which was using voltage. But in this case, voltage is equivalent to, current is equivalent to voltage over the resistance. So we can say that our I naught, our I out is equal to, if we look at this case, we have I naught. I think you should also see that the rating is, the resistance here is smaller. This is R, that's 2R, 4R, 8R, successive doubling as we go towards the most significant bit. So we have, Jimmy. So we have I naught, that would be times B3. So times B3 here, if B3 is 0, that will go. If B is 1, if B3 is 1, that will stay. As you know, you can see I naught is on its own, similar to when we had VD on its own with no fraction. Okay. And then B2 will be I naught divided by 2, but I naught is equal to V reference voltage over resistance. V reference. You can see that in this case, our I naught is V ref over R. Through here, it would be V ref over 2R. Through here, it would be V ref over 4R. And through here, it would be V ref over 8R. And so really what they've done is to factor the V ref over R out, and you stay with your fractions. And so depending on what this is, like this now B2 would go out of that equation and you would stay with the rest. Now thus far, as we complete, we have seen scenarios where the resistance keeps doubling from 1 to 2 to 4 to 8 to 16 to 32 to 64 to 128 to 256 and so on and so forth. If you have a large duct, these are 4-bit ducts. If you have a 10 duct, 20-bit duct, you're going to have a wide range of resistance values from say 1 kilo ohm to a few mega ohms. It is very difficult to precisely find, to precisely fabricate resistances that are precise over such a wide range. And so these two, while they work, they have a problem. Now there is another duct called an R2R duct, really because the resistances are between R and 2R. They are either R and 2R. This one works better, and in implementation, it is more realistic because all the resistances are either R or 2R, and that R these can be really fabricated with more precise accuracy because they are not varying over a wide range. It's like getting 1 kilo ohm and 2 kilo ohm. That's really much easier to do than getting 1 kilo ohm and 2 mega ohms for them to fall within that doubling mechanism that we talked about earlier. You don't need to remember these things, but you can see once again, you don't need to do the circuit analysis and so on. But you can see once again that we have our switch. And so if B naught is 0, the switch will connect to ground. And if B naught is 1, the switch will connect to Vref. There's a lot of circuit analysis that has already been done here, but for this 4-bit R/2R digital to analog converter, V out is equal to negative V reference over 16 times B. And this B is equivalent to B3, B2, B1, B naught. So you basically get the whole thing and convert it and get what B is. Now, generally, this is the case actually, because they can be, if it's an 8-bit duct, you won't use factor 16 here. You will need to use 2 to the power n here. Excuse me. Right. Okay. Let me see. Yeah. What if Vref is 10 volts? What are the resolution and full scale of this duct? The resolution should be got when we have B3, B2, B1, B naught being 0001. 0001. And so we are going to have our resolution being equal to, obviously, V out. It is V out. Sorry. Yeah. Okay. Yeah, somebody interrupted me. Sorry about that. Okay, so our resolution will correspond to the case of B3, B2, B1, and B0. Actually, now I cannot write. Okay. All right. B3, B2, B1, B0 is equal to 0011 or 0001. So let us see. That means our V out here will be negative Vref over 16 times B, which is 1. And Vref is 10 over 16. 1 is corresponding to B, which is 1. And so 10 over 16, I don't know what that is. V out is equal to neg 10 over 16. That will be your resolution. Then the full scale V out, full scale will be neg V ref, which is 10 over 16 times full scale. Full scale is when you have 1, 1, 1, 1, which is 15. And so your B is 15, and you get your full scale there. Okay, so that brings us to the end of our lecture. We've really done a lot. Please go and read. This is 0.625. That times 15 is neg 9.375 maybe. So yeah, so enjoy the rest of your week. Maureen and the other class representatives, tomorrow by 2 p.m. please submit that assignment. I don't want, is it tomorrow? I think it's on Friday. No excuses. I will have shared another assignment by then, hopefully, so that we can continue doing this. I'm also going to be setting something for you on Muele. So if you've not been reading, please, it is time to resume your reading. And then we will do a test towards the end of this month. I'll give a date. We are not going to negotiate too much on the date. I'll give a date because I don't have much room for negotiation, unfortunately. But I will let you know when we can have a test towards the end of the month. Have a nice day and have a nice rest of the week.